Welcome to Maths with EJD. In this video, I'll start talking about applications of eigenvalues and eigenvectors in different areas, including data science, engineering, and so on and so forth. So in this particular video, we are talking about principal component analysis in data science. So let's see what that is about. Principal component analysis, PCA, is a technique used for reducing the dimensionality of data, the dimensionality of data while preserving as much variance as possible. Okay, it helps. It helps in identifying. It helps in identifying patterns, visualizing data, and making machine learning models and making machine learning models more efficient. All right. Now, the goal, the goal, the goal of PCA is to transform the data. I mean, a given data, I'm going to demonstrate all of that. The goal of PCA is to transform the data into a new coordinate system, into a new coordinate system where axis, or what you can call principal components, axis or principal components are ordered. So in this case, since we're talking about eigenvalues and eigenvectors, right? The eigenvalues actually give us point us in the direction of the principal components because we are going to see very soon that the biggest eigenvalue points us to the first principal component, which is the eigenvector associated with the biggest eigenvalue. So a new coordinate system where axis or principal components are ordered by the variance they capture, by the variance they capture. So this is to tell us that the biggest eigenvalue captures the biggest variance. So they're ordered by the variance they capture, like that. Okay, so let's look at some steps of PCA. Steps of PCA. So the first step is to standardize the data. Standardize the data. That's the first step. So because PCA is sensitive to the scale of the data, so the first step is to standardize the data set with mean, which is mu, right, is 0, and standard deviation, which is sigma, is equal to 1. Now, imagine that you have a data set for students, right? Imagine you have a data set for students. You have, say, serial number. You have student 1, student 2, and that goes on until you have the 50th student, right? And for each of the students, you have like 10 different features, say age. So feature 1, let's say F1, age, feature 2, uh, weight, okay? feature 3, something, and all of that until you get to feature 10. So you can see that. So so the first thing you want to do, so let's imagine that that data is called X, right? So if that data is called X, you have to standardize the data. And of course, the general way of standardizing that we know is this. So given X, right? This standardized S is actually XS, which is equal to from a general idea of statistics. So that'll be something like X standardized will now be the normal X you're given, the original X minus mu, which is the mean, all over standard deviation. Of course, there are other ways of standardizing, which we're also going to learn as we proceed. Okay. So as usual, X is the original data, just like I said now, that's the original data you're given. Then XS now is the standardized data. Standardized data. Okay. So mu is the mean and sigma is the standard deviation. So that's the first step we take. Now the second step in that uh, is this. So the second step is to calculate. You calculate the covariance matrix. Calculate the covariance matrix. That's the next thing after you standardize the data. And the covariance matrix captures how each pair of features varies together. For a data set X with M features, like in our case, our data set has 10 features, age, weight, and whatever else you're interested in. So for a data set with M features, the covariance matrix is calculated as follows. So calculate the covariance using this formula. Um, Say the covariance of X is equal to 1 over n minus 1, then multiplied by the standard data transpose multiplied by the original data. Okay? I mean, multiplied by the standardized data again. So the transpose of the standardized data multiplied by the standardized data itself. So here we have a new thing where our n here, which is the new thing that's coming up, where n is the number of data points. N is the number of data points. Okay. So based on this, N is the number of data points. Okay. So based on this, right, if we come back to this table I have here, so it means that our N here is equal to 50 because there are 50 student records, and then we have 10 features. So 10 features, and then uh 10 features and 50 data points. That's what this particular table, uh, as an example, has. Okay, 10 features and 50 data points. 50 data points. Okay, that's the kind of idea. So what PCA is going to do is it is going to compress the number of features following a very strategic method, which we are following right now. So at the end of the day, instead of having 10 features, we end up having like 5 or 4, which are the most important in capturing the variance of the data set. Okay, so that's what we are doing here. Then the next thing we want to do is to compute. We want to compute eigenvalues, since we're talking about the practical applications of eigenvalues and eigenvectors. So we need eigenvalues and eigenvectors to tell us something about the data set we are given. Compute eigenvalues and eigenvectors. So eigenvalues and eigenvectors of the covariance matrix represent the amount of variance each principal component captures and the direction of those components. So the eigenvalues lambda and eigenvectors are obtained by solving the characteristic equation. So here, the eigenvalues, lambda and eigenvectors v and eigenvectors v are obtained. They are obtained by solving the characteristic equation, that is the determinant of the covariance of x minus lambda I. This is a standard way of looking for the eigenvalues, if you remember. So here we have okay, since I'm coming this way, so we can say where I is the identity matrix. I is the identity matrix. All right. So that's that. Then we go to the fourth step. For the fourth step, now since we have calculated the eigenvalues and eigenvectors up there, so the fourth step is to sort them, sort the eigenvalues, sort the eigenvalues and eigenvectors and the eigenvectors. So the eigenvalues are sorted in descending order. So the eigenvector corresponding to the largest eigenvalue is the first principal component. The second largest corresponds to the second principal component, and so on. So in essence, what we are saying is that after getting all the eigenvalues, the biggest eigenvalue, let's call that lambda max, is automatically associated with the eigenvector associated with the largest eigenvalue is automatically what you can call the first principal component, called that PC1. So this is basically, so this captures the first principal component. That means it captures the highest variance of the data set. So this is the first principal component. That's what it captures. So again, the eigenvector corresponding to the largest eigenvalue is the first. It's actually the first principal component. So the second largest corresponds to the second principal component, and so on and so forth. So if you need like five principal components, it's you just pick them. So there will be the eigenvectors corresponding with the eigenvalues you have, like that. And then we go to the fifth step. We go to the fifth step, and here what we are doing is we are choose the top k principal components. That will be determined by the number of principal components you need. Choose the top k principal components. So here you select the number of principal components k that you want to retain. This is often determined by looking at the cumulative variance explained by the components. So if at the end of the day, you need, out of the 10 features, you need maybe just 5. So what you're just going to have to do is you now have Vmax, which we can call the Vmax, right? That's like, let's call that V1, which is the first principal component. Then you have V2, you have V3, and you go on until you get to VK. VK is if you need 7, you go as far as 7. If you need 5, you go as far as 5. That's what this is about. So choose the top K principal components, whatever K is for you. Maybe out of the 10 features, you want 8 or 7, at the end of the day. So you just go in that order. Then we go to the sixth step. So for the sixth step, we have this. You now project the data. Project the data. Okay. So that is where you now have the new form of the data after applying principal component. So the original data is projected onto the selected principal components to obtain the transformed data. So formula for projecting data now is this. That is the x transformed x will be equal to, okay, now we have xt, okay, xt equals xs, that's the standardized data, multiplied by the vk you would have chosen up there. So you can now say where xt is the transformed data, that's the transformation that has been done by PCA, transformed data by PCA, and VK is the matrix. It is actually the matrix of the first K eigenvectors. Okay, so if you ended up picking 4 eigenvectors based on the fact that you needed 4 principal components, you're going to have a 4x4 matrix. It all depends on what you want. Now let's take an example to drive home this idea. So imagine, okay, I've been using this a lot. So example, so I'll take a very simple example so you can always apply it in whatever situation you have. So consider a simple two-dimensional data set, which is X, and that is 2, 3, 3, 4, 4, 5, 5, 6, and 6, 7. So this is the X we actually have here. Okay, so consider this. Of course, as you can see, this is like this data has just two features. So you have F1, F2, those are the two features. And how many data points now? We have N1, if you like, we can call that N1. This is N2, N3, N4, and N5. Okay, so here we have, so we say this data set has two features. Okay, more like maybe the first feature is maybe something like age, the second one is weight, whatever. So you can do that for any kind of data. So this data set has two features and five data points. Okay, that's important to note. Two features and five data points. So with that now, what do? Let's follow the steps. So now step one here. Step one, you already know step one is to standardize the data. Standardize the data. Okay. Now, what does it mean to standardize the data? So what we do first is to calculate the mean of each column. The mean of each column. Calculate the mean of each column. So that will give us mu1 to be, so the first column is where you have 2, 3, 4, 5, 6. So you have 2 plus 3 plus 4 plus 5 plus 6 divided by 5. So because we have 5 data points, 2 plus 3, 5, 5 plus 4, 9, 9 plus 5, 14 plus 6, 20 divided by 5. So mu1 is 4. That's the mean of the first column. Then we do second column, mu2. For mu2, we have 3 to 7, right? 3, 4, 5, 6, 7. So we have 3 plus 4 plus 5 plus 6 plus 7 divided by 5 again. 3 plus 4 is 7 plus 5, 12 plus 6, 18 plus 7, that's 25 divided by 5. So mu2 is 5. Now, having done that, the next thing is to subtract. Now, subtract the mean. Subtract the mean from each column. Subtract the mean from each column to standardize the data. Okay, so that's how we standardize it, not instead of the following that general rule we know. So now we are going to have our X standardized to be as follows. So imagine that you have, okay, I can just put everything together. So, you have two, for the first column, 4 is the mean, 2 minus 4, 3 minus 4, 4 minus 4, 5 minus 4, and then 6 minus 4. That's for the first column. Okay. So for the second column, we have 3 minus 5, 4 minus 5, 5 minus 5, 6 minus 5, and 7 minus 5. So that's how we standardize in this situation. And then we have 2 minus 4 is minus 2, minus 2. 3 minus 4 is minus 1. 4 minus 4 is 0. 5 minus 4 is 1. 6 minus 4 is 2. Next, 3 minus 5 is minus 2. 4 minus 5 is minus 1. 5 minus 5 is 0. 6 minus 5 is 1. 7 minus 5 is 2. So we have the standardized data right there. So that's first step done. So let's go for the second step. So step 2 now. For step 2, we calculate the covariance matrix. Calculate the covariance matrix. Okay. So the covariance matrix is given as, we have cov x equals 1 over n minus 1 x standard transpose xs. Okay. So what that simply means is that we have covariance of x to be number of data points we have based on the data is 5, right? 1, 2, 3, 4, 5. That's the number of data points we have. That's 5. So we have 1 over 5 minus 1. Then xs transpose. Xs transpose, this is xs, right? So if you transpose it, this is column 1, this is column 2. So in transposing, right, column 1 becomes row 1, okay? And column 2 becomes row 2. So that means XS transpose is going to be something like -2, -1, 0, 1, 2. Of course, -2, -1, 0, 1, 2. So that's against -2, -2, -1, -1, 0, 0, 1, 1, and 2, 2. And that is what we have right there. Okay. So means that the covariance of X is equal to 1 over 4. Then we have to now deal with all of this. Just like this smart way I like to multiply matrices, right? So what you do first is this one has 2 rows, I mean 2 columns, and this one has 2 rows. Because it has 2 rows, you have to write each column twice. So that means you are going to have -2, -1, 0, 1, 2. Then -2, -1, 0, 1, 2. Then that's for the first row now. For the second row, you have -2, -1, 0, 1, 2. Then -2, -1, 0, 1, 2. So then you can now invert this one, the columns, I mean the rows here over them. So that one at the top, you invert it over the first row. That's -2, -1, 0, 1, 2. Then -2, -1, 0, 1, 2. Then, of course, the second one also goes in the same manner. So this one now goes to the second row. So we have -2, -1, 0, 1, 2. -2, -1, 0, 1, 2. Okay. So we have this. Interestingly, they are all the same, so it's easy to move on from here. So the covariance of X now is 1 over 4 into, so -2 times -2, that's 4. -1 times -1, that's 1. So 4 plus 1 is 5. 0 times 0 is 0. 1 times 1 is 1. So 5 plus 1, 6. 2 times 2 is 4 again. So each one is 10. So we have 10, 10, 10, 10 all the way. Then it means that the covariance of X is equal to 10 over 4, 10 over 4, 10 over 4, and 10 over 4, which means that each of this will just be 5 over 2, all the way 5 over 2, 5 over 2, 5 over 2, which is 2.5. But I like working with fractions, right? So you should take note of the strategic things we've been getting. This is really important. This is really important. The standardized data set, this is important. Then the covariance of X we have also got now is really important because it helps at the next level. Then I could make it 2.5 each, but I'm leaving it as fraction because that preserves the value. Okay. Now we move on to compute eigenvalues and eigenvectors. So that's the next thing we want to do. So to compute eigenvalues and eigenvectors, that is step 3. Compute eigenvalues and eigenvectors. So this actually shows us the principal components. And that's why it's called principal component analysis. So compute eigenvalues and eigenvectors. Now, how do you do that? The formula for that is the covariance of X minus lambda I equals 0. So right now we don't know what the lambda is, right? So the covariance of X, we already know that is 5 over 2, 5 over 2, 5 over 2, 5 over 2, minus lambda I, that's simply lambda 0, 0, lambda, like this. And all of that is equal to 0. So that means we have the determinant of 5 over 2 minus lambda, then 5 over 2 here. Then here we have 5 over 2 again. This is 5 over 2 minus lambda. All of this is equal to 0. So since we are taking the determinants, so it means we can cross multiply. So we have, so let me just change inks here. Let me go green. So we have 5 over 2 minus lambda into 5 over 2 minus lambda. That's this multiplied by this minus this multiplied by this. That's 5 over 2 into 5 over 2. And all of that is equal to 0. So, of course, that's more like 5 over 2 minus lambda squared minus 5 over 2 squared. That is 0. And, to do this one, right, if you follow my mental matrix, we have a smart way of doing this. To expand this now, you just have 5 over 2 squared minus 2 into 5 over 2 multiplied by minus lambda. Do I have to put minus lambda there? No, that's not necessary because we already have the minus outside. So this is just lambda, then plus lambda squared. then this minus 5 over 2 all squared equals 0. So here, this is 25 over 4 minus, 2 cancels 2 now. That's minus 5 lambda plus lambda squared. Then this is minus 25 over 4 equals 0. Interestingly, that looks really easy to move on. So let me go black now. So this cancel this easily. So we just have lambda squared minus 5 lambda. I mean, this is easier than I expected. Lambda squared minus 5 lambda equals 0. So now we have lambda into lambda minus 5 equals 0. So we have lambda equals 0 or lambda minus 5 equals 0. That means lambda is equal to 0 or lambda is equal to 5. So of course, because, okay, let me see if we are supposed to do that. Okay, I mean, we have got our lambdas, right? So we can just conclude that therefore lambda is either 0 or 5. Okay, those are the two lambdas we have got. So the next step is where we sort them. So we have step 4 now. Step 4, sort eigenvalues and eigenvectors. Sort eigenvalues and eigenvectors. Okay, so to do that, so we can see that the eigenvalues are sorted in descending order. That's from the, rather, it should be in descending order. That's from the biggest to the smallest in descending order. So if we do that, that means the bigger of the two is lambda 1, which is 5, and then lambda 2 is equal to 0. So that tells us, so we can say, so those are the eigenvalues, right? So we now need to find the eigenvectors, which correspond with this. Actually, up there, we're supposed to find the eigenvalues and eigenvectors, but maybe we can continue with that here now. So if we want to find eigenvectors, the way to go is, so we have to come back to this level, right? So let's talk about, okay, let's find the eigenvectors. Let me not jump because we need both together, right? Let's compute the eigenvectors, right? Okay, so, okay, so let me just go and say, to compute the eigenvectors, to compute the eigenvectors, so, um, we need something like this. We need the covariance of x minus lambda I, multiply. So the eigenvectors are now v, and all of that will be equal to 0. And from what we know already, so this will just be 5 over 2 minus lambda, 5 over 2 minus lambda. I think this should be determinant, okay? I think we need the determinant. Yes, I think. So 5 over 2 minus lambda, then 5 over 2. And this is 5 over 2 again, then 5 over 2 minus lambda. Okay. So that multiplied by, okay, I don't think it has to be determinant. I don't think it has to be determinant. It's just the brackets. Okay. It's the brackets. It's the brackets. So, okay. So we have, so from covariance minus lambda, we already know this is 5 over 2 minus lambda. This is 5 over 2. This is 5 over 2. This is 5 over 2 minus lambda, and that is into the vector 1, vector 2, v1, v2, and that is equal to 0. But of course, we already know how that works. So we can say for lambda equals 0, we have 5 over 2. So everything is 5 over 2 all the way. So for lambda equals 0, we have 5 over 2 everywhere. 5 over 2, 5 over 2, 5 over 2 into v1, v2. equals 0, 0. Okay, that's how that works. Of course, this should have been 0, 0 also. Okay. So, I mean, from what we have here, right, it's obvious that that is just 5 over 2 V1 plus 5 over 2 V2 equals 0. Even the second one is like that. If you multiply through by 2 over 5, you just get V1 plus V2 equals 0. That's if you multiply through by 2 over 5. So, or you divide through by 5 over 2, it's the same. So here now you can now say, so if you take, if you let, okay, that simply means that V2 is equal to, uh, yeah, V2 is equal to minus V1, as we know. So we can now choose any value arbitrarily. So if V1 is equal to 1, so that means V2 is equal to minus 1. So we are going to have the eigenpair. So the eigenpair here, the eigenpair is, so the eigenpair would be the eigenvalue, which is 0, that give us that, into 1 minus 1. That's the eigenpair for this. So an eigenpair is the putting together of the eigenvalue, and this is the eigenvector, which is the principal component. But of course, we know 0 is smaller than 5. So it can be the first principal component. So this is the eigenvector corresponding to it, right? So we can even put transpose on top of it. So that is for lambda equals 0. So if we do for lambda equals 5, so it means we have 5 over 2 minus 5, then 5 over 2, then this is 5 over 2, and this is 5 over 2 minus 5 again. And all of that into V1, V2, and that is equal to 0, 0 now. So 5 over 2 minus 5 is actually that's 2.5 minus 5, right? That's minus 2.5. So this will be minus 5 over 2. This is 5 over 2. Then this is 5 over 2 again. And this is minus 5 over 2. All right, that's 5 over 2 minus 5 over 1. LCM is 2. 2 into that's 5 minus 1 is 2. 2. 2 times 5, 10. So that's minus 5 over 2. That's how I got all of that. Okay. So, and this is equal to, so all that multiplied by V1, V2, and that is equal to 0, 0. Okay. So we can now multiply. So if we multiply again, we have minus 5 over 2 V1, okay, plus 5 over 2 V2. That's this together with this now. So this multiplies this and this multiplies this. So, and all of that is equal to 0. So, so if we tidy up this, that means 5 over 2 V2 is equal to 5 over 2 V1. In short, 5 over 2 cancels out. So V2 is equal to V1, okay? So if we also do the second one, it gives us exactly the same, because that's just going to be 5 over 2 V1 minus 5 over 2 V2, okay? Equals 0. So that means that 5 over 2 V1 again is equal to 5 over 2 V2. So that cancels out. So V1 is still V2. Okay. So in this case, the eigenpair is eigenvalue is 5, and the eigenvector. Okay, I mean, before I even talk about the eigenpair, we should get the eigenvector. I'm not done. So we already know they are equal, right? So with the fact that V1 is equal to V2, that means we are going to say that if V2 is equal to 1, V1 is also equal to 1. So, what? Okay, so here, normally I should have just said this, that implies that V1, V2 is equal to 1 minus 1, okay? All right, so here too, this simply implies that V1, V2 is equal to 1, 1, okay? So the eigenpair here is eigenvalue 5 then eigenvector 1, 1 transpose. So that's what we have. So we can now go to step 4, which is ordering. So we order the eigenvalues. Now, because we have a 2 by 2 matrix here, so it's easy to just have what we have now. But in case you have like a 5 by 5 matrix, you're going to have 5 eigenvalues most likely. So now we are going to have sort. So step 5, or is it step 4? Step 4, sort eigenvalues and eigenvectors and eigenvectors. So like that. So of course, the eigenvalues are sorted in descending order. Okay. So that means that lambda 1 will be 5 and lambda 2 will be 0 because we start from the biggest. Thus, the first principal component corresponds to the eigenvector v1, which will be equal to 1, 1. Okay, that's what corresponds to 5. That's the eigenpair for 5, 1, 1. Okay, and the second principal component corresponds to the eigenvector v2, which is equal to 1 minus 1. Okay, those are the only two we have. If you have more, you can keep arranging them like that. So we can go to step 5 now. Step 5. So we can choose the top k principal component. So we have only two here. Maybe we can choose only one. So choose the top k principal components. Trying to squeeze that in, but it's not working. So choose the top k principal components. So of course that's easy peasy, right? Since lambda 1 is much larger than lambda 2, we choose k equals 1 principal component. K equals 1 principal component to retain most of the variance. So eigenvalue 5 and eigenvalue 0 tells you eigenvalue 5 retains most of the variance. So we go to step 6 as we draw to a close. Step 6 is where we project the data. Okay. So, and to project the data, so just like we said, the transformed data which we are looking for is actually the standardized data multiplied by V1. So because we are talking about only VK here, we have only one principal component that we have chosen. So okay, so we just do that. So again, we go back and see that X transpose is XS. If you remember where we started from, that's -2, -2, -1, -1, 0, 0, 1, 1, and 2, 2. All of that multiplied by 1, 1. Okay. So what this simply means is that we have X transpose to be. So you can see we have just a column vector, and then there are 2 rows each here. So we have 2 rows each. We have this and 2 rows each. So it means you're going to, how many rows do we have? 1, 2, 3, 4, 5. So you're going to write 1, 1 5 times. So you have 1, 1, 1, 1, 2, 1, 1, 3. Okay, let me give some space. 1, 1, 4, 1, 1, 5. So then you now put all those things over it. So that would be -2, -2, -1, -1. Then you have 0, 0, and then you have 1, 1, and then you have 2, 2. Okay. So you started with a 5 by 2 matrix, and you're ending with a 5 by 1 matrix. So that way you have dropped one column that is not that important. That's the essence of principal component analysis. So here now we have -2. Okay, let me just go. So this is -2 for the first one. That one times -2. Then this is next -1 -1. Next you have 0 plus 0. Next you have 1 plus 1. Next you have 2 plus 2. Okay, so that I guess that's, yeah, that's what we have. Okay. Yeah, that's what we have. So that our X transpose now, X transpose, I mean X transformed rather, the transformed data using principal component analysis can now be this. So -2, that's -4 up here. That's -4. Then -1 is -2. Then 0 plus 0 is 0. 1 plus 1 is 2. Then 2 plus 2 is 4. So this is our transformed data right now. And that is the deal. So now, this is the final result. This is the final result of principal component analysis, where the data has been reduced. The data has been reduced to a single principal component, to a single principal component. Okay. And that's the essence of what we have here. So if you have a wider dimension, it would have been something, so you'd have had it more robust than this, right? But this gives a brief of all that. So in summary, right, we see that reduces, PCA reduces the dimensionality of the data set, from 2D, from 2 dimensions to 1 dimension. That's the first point. The second point is that we retained the most important, the most important variance along the first principal component, And that is one very vital application of eigenvalues and eigenvectors, in data science, talking about principal component analysis. So if you have subscribed to this channel, thank you. If you have not, go ahead and do that right here and hit the notification bell so you can always get alerted every time a new video is released. Also, comment, let me know how helpful this video is for you. Let me also know if there's a topic you'd like me to teach, or a problem you'd like me to solve. Then like and share so that more people can have access to this great content. Till I come your way again, keep doing maths right. Bye.